Tonight, we're going to confront something that sounds straightforward, but will quietly rearrange the way you think about the universe. Alpha Centauri. You've heard the name before. It's our nearest stellar neighbor, the closest star system to our own. And because it's the closest, most people assume it must be somehow reachable, somehow within our grasp. But here's what almost nobody truly understands. The distance between us and Alpha Centauri is so staggeringly vast that even calling it the nearest star system is almost misleading. It gives you a sense of closeness that doesn't exist. When you actually break down what that distance means, when you compare it to everything humans have ever known or traveled, it changes something inside you. And by the end of tonight, you'll understand exactly why. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now let's begin. Let's start with something you already understand. Distance. You deal with distance every single day of your life and you barely think about it. The walk from your bedroom to your kitchen, the drive to work, the trip to the nearest grocery store. These are distances your brain handles effortlessly because your brain evolved to manage exactly these kinds of measurements. A few steps, a few blocks, a few miles, distances you can see, distances you can walk, distances that connect one part of your daily routine to another. If someone tells you a coffee shop is 2 miles away, you have an immediate intuitive sense of what that means. You know it's too far to walk comfortably, but close enough to drive in a few minutes. If someone says a city is 300 miles away, you can picture that too. That's a 5 or 6 hour drive. You'll want to fill up the gas tank, maybe pack a lunch, plan for a rest stop along the way. These distances are built for human understanding because they exist at a human scale. We evolved on the African savanna tracking game across plains that stretch for dozens of miles. We learned to navigate between water sources and shelter across distances we could cross on foot in a day or two. Our sense of distance is calibrated for survival on the surface of a planet, and it works beautifully for that purpose. But tonight, we're going to push far beyond that comfort zone. We're going to scale upward, step by step, from the distances you know to distances that will make your brain quietly give up trying to visualize them. And we need to do this because without building that ladder, without climbing it rung by rung, there's no way to appreciate what we're actually talking about when we say the words Alpha Centauri. So let's start climbing. The circumference of Earth at the equator is about 40,075 kilometers. That's the distance you would travel if you could walk in a perfectly straight line around the entire planet, crossing oceans and mountains and deserts, and end up right back where you started. It's a big number, but it's not an incomprehensible one. Humans have been circumnavigating the globe for over 500 years. Ferdinand Magellan's expedition left Spain in 1519, and what remained of his crew returned in 1522, having sailed all the way around the world in about 3 years. Modern commercial jets can circle the Earth in roughly 45 hours of continuous flight. Earth is large from where you're standing on its surface, but it's a finite, knowable place. You could in theory visit every part of it in a single lifetime if you dedicated yourself to the task. Every mountain, every coastline, every forest and desert is reachable. Earth is big enough to feel enormous, but small enough to be fully explored. Keep that feeling in mind because it's about to change. The moon orbits Earth at an average distance of about 3 184,000 kilometers. That number might not mean much on its own, so let me frame it differently. If you could somehow drive a car to the moon at highway speed, say 100 kilometers per hour without stopping, it would take you about 160 days. Over 5 months of continuous driving just to reach the nearest object in space. The Apollo astronauts, using some of the most powerful rockets ever built at the time, traveling at speeds of roughly 11 kilometers per second, still needed about 3 days to make the journey. 3 days in a spacecraft hurtling through the void at nearly 40,000 kilometers per hour. And that's just to the moon. The moon is so close to Earth that you can see it with your naked eye every night. You can see craters and dark patches on its surface with a pair of cheap binoculars. It's right there, hanging in the sky, looking close enough to touch. And yet, it takes 3 days of rocket-powered travel to reach it. When the Apollo astronauts spoke to mission control from the lunar surface, there was a delay of about 1.3 seconds each way. Their words, carried by radio signals traveling at the speed of light, still needed over a second across the gap between the moon and Earth. That delay is subtle but real. You can hear it in the recordings. There's always a pause, a lag, a gap built into every exchange, because even light, the fastest thing in the universe, needs time to cross that distance. This is important to understand early on. Even at the scale of the Earth and Moon, distances in space are already enormous compared to anything in your daily life. And we haven't even left our own planet's immediate neighborhood yet. Now, let's take a much bigger step. The Sun sits at an average distance of about 150 million kilometers from Earth. Astronomers call this distance 1 astronomical unit, or AU. It's a convenient shorthand because the number itself is so large that saying it out loud every time gets exhausting. 150 million kilometers. If you tried to drive to the Sun at highway speed, it would take you roughly 170 years. Not months, years. Nearly 2 full human lifetimes spent driving without sleep, without food, without stopping, just to reach the star that lights our sky every morning. Light covers this distance in about 8 minutes and 20 seconds. That means when you look at the Sun, you're not seeing it as it is right now. You're seeing it as it was over 8 minutes ago. If the Sun suddenly vanished this very second, you would continue to see it shining in the sky for another 8 minutes and 20 seconds. You'd feel its warmth. You'd see its light. Everything would seem perfectly normal. And only after those 8 minutes passed would the sky suddenly go dark. And you'd realize that the Sun was already gone before you even knew something was wrong. This is a distance so vast that even light, traveling at 300,000 kilometers every single second, needs over 8 minutes to cross it. And the Sun is close. It's our star. It's right here in our cosmic backyard. Everything on Earth depends on it. Every plant, every animal, every weather pattern, every ocean current, all of it is driven by energy that travels 150 million kilometers across empty space to reach us. The Sun dominates our sky and our lives, and yet it's already far enough away that the distance begins to feel abstract. You can write down 150 million kilometers, but you can't really picture it. There's nothing in your lived experience that corresponds to a distance like that. Let's keep going outward. Mars, at its closest approach to Earth, is about 55 million kilometers away. At its farthest, when Earth and Mars are on opposite sides of the Sun, that distance stretches to about 400 million kilometers. When NASA sends commands to the Perseverance rover operating on the Martian surface, Those commands travel at the speed of light and still take between 3 and 22 minutes to arrive depending on where Mars is in its orbit. If the rover encounters a problem, if it gets stuck on a rock or its instruments detect something unexpected, mission controllers on Earth won't know about it for minutes, and their response, once they figure out a solution, takes another 3 to 22 minutes to reach Mars. A problem that you could solve in seconds with a remote control car on Earth can take an hour or more to address on Mars. This is what real distance in space looks like. Even within our own solar system, even dealing with a neighboring planet that we can see with the naked eye on a clear night, the distances are so large that real-time interaction becomes impossible. You can't have a conversation with Mars. You can only exchange messages and wait. Jupiter, the largest planet in our solar system, orbits at an average distance of about 778 million kilometers from the Sun. That's roughly 5.2 astronomical units. When the Juno spacecraft arrived at Jupiter in 2016, after a 5-year journey, communication signals took between 33 and 53 minutes to travel between the spacecraft and Earth. Every image Juno captured, every piece of data it collected, took the better part of an hour to reach the scientist waiting to see it. The spacecraft had to operate largely on its own, following pre-programmed sequences, because there was no possibility of real-time guidance from Earth. Saturn is even farther out. At about 1.4 billion kilometers from the Sun, roughly 9.5 astronomical units. Saturn is so distant that the Cassini spacecraft, which orbited it from 2004 to 2017, experienced communication delays of over an hour. Cassini couldn't be steered like a car or piloted like a drone. Engineers had to plan entire sequences of observations days or weeks in advance, upload them to the spacecraft, and trust that everything would work. If something went wrong, Cassini had to be smart enough to handle it on its own, because by the time Earth learned about the problem and sent new instructions, more than 2 hours would have passed. The situation could have changed completely by then. Neptune, the most distant planet in our solar system, orbits at about 4.5 billion kilometers from the Sun, roughly 30 astronomical units. When Voyager 2 flew past Neptune in 1989, the only spacecraft ever to visit this distant ice giant, communication signals took over 4 hours each way. The data from that flyby, the images of Neptune's blue atmosphere and its strange moon Triton, crawled across billions of kilometers of empty space at the speed of light, and still took 4 hours to reach Earth. 4 hours for light to travel from Neptune to your eyes. Think about that. Light, the fastest thing in the universe, moving at 300,000 kilometers every single second, needs 4 hours to cross the distance between Neptune and Earth. And we're still inside our own solar system. We haven't left home yet. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies stretching from about 30 to 50 astronomical units from the Sun. Pluto, the most famous resident of this region, orbits at an average distance of roughly 5.9 billion kilometers from the Sun. When the New Horizons spacecraft flew past Pluto in July of 2015, after a journey that took 9.5 years, communication signals took about 4.5 hours each way. The entire flyby was automated. Every observation, every photograph, every measurement was pre-programmed months in advance. Mission controllers could not react to what New Horizons was seeing in real time. They had to trust the plan and wait. But even the Kuiper Belt is not the edge of our solar system. Far, Beyond it, stretching outward to staggering distances, lies the Oort Cloud. This vast spherical shell of icy objects surrounds the entire solar system like a cosmic bubble. The inner edge of the Oort Cloud begins at roughly 2,000 astronomical units from the Sun, and the outer edge extends to perhaps 100,000 astronomical units. That outer boundary is nearly 2 light years from the Sun. 2 light years. That means light leaving the Sun right now would take 2 full years to reach the outermost object still gravitationally bound to our star. No spacecraft has ever reached the Oort Cloud. No human eye has ever directly seen an Oort Cloud object in place. We know it exists because long-period comets occasionally fall inward from this distant region, their icy surfaces vaporizing as they approach the Sun's warmth. But the Oort Cloud itself remains unvisited, unexplored, a vast frontier that defines the true boundary of the Sun's gravitational domain. And this brings us to Voyager 1, the most distant human-made object in existence. Voyager 1 launched in 1977. It has been traveling through space for nearly 50 years, moving at about 17 kilometers per second. That's roughly 61,000 kilometers per hour. At that speed, you could cross the entire United States in about 4.5 minutes. Voyager 1 is moving incredibly fast by any human standard. And yet, after nearly 5 decades of constant travel through the vacuum of space, with nothing to slow it down, no friction, no air resistance, nothing, Voyager 1 is currently only about 24 light hours from Earth. That's roughly 1 light day. In 50 years of non-stop travel at breathtaking speed, Voyager has covered a distance that light crosses in a single day. Let that sink in for a moment. Our fastest, most distant explorer, the pinnacle of human engineering launched nearly half a century ago, has traveled a distance that light covers between breakfast and breakfast. And where is Voyager 1 now? It crossed the heliopause in 2012, the boundary where the solar wind finally gives way to the interstellar medium. It has technically entered interstellar space, the space between stars. That was celebrated as a historic milestone, and it was. Voyager 1 became the first human-made object to leave the Sun's protective bubble and enter the void between stellar systems. But here's the sobering reality. Voyager 1 is still laughably close to home by cosmic standards. It hasn't reached the Oort Cloud yet. It won't enter the inner Oort Cloud for roughly another 500 years. It won't pass through the outer Oort Cloud for perhaps another 30,000 years. After 50 years of travel, Voyager hasn't even finished leaving the Sun's extended neighborhood. It's like walking out your front door and declaring you've left the city when you're still standing in your driveway. The solar system, when you include the full extent of the Oort Cloud, is enormous. It spans nearly 2 light years in radius, and everything we have ever explored, every planet we've photographed, every moon we've landed on, every asteroid and comet we've studied, all of it exists in a tiny region near the center of this vast structure. The planets, all 8 of them, from Mercury to Neptune, fit within roughly 30 astronomical units of the Sun. That's a sphere about 9 hours wide at light speed. The Oort Cloud extends that boundary to nearly 2 light years. The explore part of our solar system is like a single room in a house the size of a city. This is the crucial foundation for everything that comes next. Because if you don't truly understand how large our own solar system is, if you don't feel in your bones how vast the distances are even between neighboring planets, then the distance to Alpha Centauri won't mean anything to you. It will just be another big number. And big numbers by themselves are meaningless. They don't teach you anything. They don't change how you see the universe. What changes your perspective is understanding scale. Understanding how one distance compares to another. Understanding that a distance which already seemed impossibly large is actually tiny compared to what comes next. So here's where we stand. We've climbed the ladder from the distances you walk every day to the distance across Earth, to the moon, to the sun, out past Mars and Jupiter and Saturn and Neptune, through the Kuiper Belt and into the theoretical reaches of the Oort Cloud. At every step, the distances have grown larger, more difficult to imagine, more removed from anything in ordinary human experience. The moon seemed far at 384,000 kilometers. The sun seemed absurdly distant at 150 million kilometers. Neptune pushed the boundaries at 4.5 billion kilometers. The outer Oort Cloud, at nearly 2 light years, stretches the solar system to a scale that makes the planetary orbits look like they're sitting on top of each other. And everything we've talked about so far, every kilometer, every astronomical unit, every light minute and light hour, all of it exists within the domain of a single star. Our star, the sun. All of it is local. All of it is home. The farthest humans have ever sent anything, Voyager 1, is still so close to the sun that in a model of the galaxy, you couldn't distinguish it from the sun's position. It's like 2 grains of sand touching each other on a beach that stretches from coast to coast. Now we need to cross the gap. We need to leave the sun's territory entirely and travel across interstellar space, the vast emptiness between stars, to reach the nearest other stellar system, Alpha Centauri, our closest neighbor among the hundreds of billions of stars in the Milky Way, the star system that bears the title of nearest to our own. And when you see how far it actually is, when you measure that distance, against everything we've just discussed, you'll understand why that title, nearest, is one of the most deceptive words in all of astronomy. Because nearest in this case doesn't mean close, it doesn't mean reachable, it doesn't mean anything resembling what your brain imagines when it hears the word near. The distance to Alpha Centauri is going to take every concept we've built tonight, every scale we've established, every comparison we've made, and it's going to shatter them. And that's exactly where we're going next. So let's talk about what we're actually pointing at when we say Alpha Centauri. Because most people hear that name and picture a single star, one bright point of light hanging in the southern sky, our nearest neighbor. But that's not what Alpha Centauri is. Alpha Centauri is a system. It's a family of stars, 3 of them bound together by gravity, orbiting and drifting through space as a unit. And understanding what this system actually looks like, what it's made of, and how its members relate to each other matters because it gives you a sense of the place we're measuring the distance to. It's not just a dot on a chart, it's a real physical structure with real stars and real distances within it. And it's been sitting there, burning steadily, for billions of years, completely indifferent to the fact that it happens to be the nearest stellar system to our own. The 2 main stars in the system are Alpha Centauri A and Alpha Centauri B. These are both sun-like stars, which means they're broadly similar to the star that lights our sky every morning. Alpha Centauri A is the larger and brighter of the 2. It's about 10% more massive than our sun, and roughly 50% more luminous. If you could stand on a hypothetical planet orbiting Alpha Centauri A at the same distance Earth orbits the sun, the star would look similar to our sun, but noticeably brighter and slightly more yellow-white. It's a G-type main sequence star, the same classification as the Sun, burning hydrogen in its core through the same nuclear fusion process that powers every star in the universe. Alpha Centauri b is a bit smaller and cooler. It has about 90% of the Sun's mass and only about half the Sun's luminosity. It's classified as a K-type main sequence star, which makes it slightly more orange in color than the Sun. If you could see it up close, Alpha Centauri b would look like a warm, steady orange-tinted sun, dimmer than what we're used to, but still a perfectly respectable star by any standard. Both of these stars are roughly the same age as the Sun, around 4.5 to 6 billion years old, meaning they formed around the same time as our solar system or perhaps a bit earlier. They've been burning steadily for billions of years and will continue to do so for billions more. These two stars orbit each other. They're locked in a gravitational dance that takes about 79.9 years to complete. Their orbit is elliptical, meaning the distance between them changes over time. At their closest approach, called periastron, Alpha Centauri A and B are about 11 astronomical units apart. That's roughly the distance from the Sun to Saturn. At their farthest, called apastron, they separate to about 36 astronomical units. That's close to the distance from the Sun to Pluto. So these two stars spend their lives swinging back and forth between roughly Saturn's distance and Pluto's distance from each other. If you were standing on a planet orbiting one of them, the other star would be clearly visible in the sky. Not just as a point of light, but as a brilliant star, far brighter than anything in Earth's night sky. At closest approach, Alpha Centauri b, as seen from a planet orbiting Alpha Centauri a, would blaze thousands of times brighter than the full moon appears from Earth. It would cast sharp, distinct shadows at night and be clearly visible even during the day, a second sun too small to show a disk, but far too bright to ignore. You would live in a binary star system, and you would know it every single evening. Then, there's the third member of the family, Proxima Centauri. This star is much smaller, much dimmer, and much farther from the other two than most people realize. Proxima Centauri is a red dwarf, the most common type of star in the entire Milky Way galaxy. Red dwarfs make up roughly 70% of all stars, yet not a single one of them is visible to the naked eye from Earth. They're simply too dim. Proxima Centauri has only about 12% of the Sun's mass and roughly 14% of its diameter. If you place the Sun and Proxima Centauri side by side, the Sun would tower over it. Proxima Centauri produces only about 0.17% of the Sun's luminosity. It's so faint that despite being the closest star to our solar system, you need a telescope to see it. You could stand outside on the darkest, clearest night in the most remote location on Earth, and you would never spot Proxima Centauri with your eyes alone. It's invisible to us without technology. Proxima Centauri orbits the Alpha Centauri A and B pair at a tremendous distance. It sits roughly 13,000 astronomical units from the central pair. That's about 0.2 light years. To put that in perspective, 13,000 astronomical units is roughly 1/5 of a light year, or about 2 trillion kilometers. That's a staggering distance just between members of the same star system. Proxima Centauri is so far from Alpha Centauri A and B that its orbital period around them is estimated at roughly 547,000 years. More than 500,000 years for one single orbit. It crawls around its distant companion so slowly that from a human perspective, it barely moves at all. Some astronomers have even debated whether Proxima Centauri is truly gravitationally bound to the other two or simply passing through the same region of space. More recent observations suggest it is genuinely bound, that it's a true member of the system, but its connection is tenuous. It clings to the system's edge like a satellite barely held in orbit. Now, Proxima Centauri is notable for one particular reason, beyond its proximity to us. It's actually the closest individual star to our Sun, not Alpha Centauri A, not Alpha Centauri B, but Proxima. Because of its wide orbit around the central pair, Proxima Centauri currently sits slightly closer to us than its companions. The distance to Proxima Centauri is about 4.24 light-years. The distance to Alpha Centauri A and B is about 4.37 light-years. The difference is small, roughly 0.13 light-years, but it's enough to earn Proxima Centauri the title of the nearest star to our Sun. When people casually refer to the nearest star, they usually mean Proxima Centauri. When they refer to the nearest star system, they mean the entire Alpha Centauri system, including all three stars. Proxima Centauri is also known to have at least 2 planets. Proxima Centauri b, discovered in 2016, orbits in the star's habitable zone, the region where temperatures could theoretically allow liquid water to exist on a planet's surface. This discovery generated enormous excitement because it meant the nearest star to us hosts a potentially Earth-like world. But the excitement comes with heavy caveats. Proxima Centauri is a flare star. It periodically unleashes violent outbursts of energy, sudden flares that can temporarily increase its brightness by a factor of several hundred in ultraviolet and X-ray wavelengths. These flares blast any nearby planets with intense radiation. In 2018, astronomers detected a super flare from Proxima Centauri that was roughly 10 times more powerful than the largest solar flares our Sun has ever produced. A planet in the habitable zone of Proxima Centauri would be bombarded by this radiation regularly. Over time, these flares could strip away a planet's atmosphere, sterilize its surface, or both. So while Proxima Centauri b orbits in the habitable zone, the word habitable might be generous. The environment around a flare star is harsh in ways that our own solar system simply isn't. So that's the system. 3 stars, 2 sun-like stars locked in a roughly 80-year orbital dance. 1 tiny red dwarf trailing along an immense distance, hosting at least 2 planets but bathing them in periodic blasts of radiation. A real place, a complex gravitational family, burning steadily in the southern sky for billions of years. And the whole thing sits at the distance we now need to understand. Because knowing what Alpha Centauri is only matters if you understand how far away it is. And that distance is where everything changes. But before we talk about what that distance means, it's worth pausing to ask a more basic question. How do we actually know how far away Alpha Centauri is? You can't stretch a measuring tape across 4 light-years of empty space. You can't bounce a radar signal off another star the way you can off the moon or a nearby planet. The distance is far too great for any direct measurement like that. A radar pulse sent toward Alpha Centauri would take over 8.5 years to make the round trip, and by the time it returned, the signal would be so unimaginably faint that no instrument on Earth could detect it. So astronomers had to find another way. And the method they developed is both beautifully simple in concept and maddeningly difficult in practice. It's called stellar parallax. Here's how it works. Hold your thumb out at arm's length and close one eye. Now switch eyes. Your thumb appears to jump to the side against the background behind it. That apparent shift is called parallax, and it happens because your two eyes see your thumb from slightly different angles. The farther away an object is, the smaller its parallax shift becomes. Now apply this same principle to stars. Instead of using two eyes separated by a few inches, astronomers use two observations of the same star, taken 6 months apart, when Earth is on opposite sides of its orbit around the Sun. The diameter of Earth's orbit is about 300 million kilometers. That's the baseline. When you observe a nearby star in January and then observe it again in July from the other side of Earth's orbit, the star appears to shift very slightly against the background of much more distant stars. By measuring this tiny angular shift, you can calculate the star's distance using basic trigonometry. The concept is straightforward. The execution is extraordinarily hard, because the angular shifts involved are minuscule. Even for the closest stars, the parallax angle is less than 1 arcsecond. An arcsecond is 1/3600th of a degree. Imagine dividing a single degree of arc, which is already tiny, into 3600 equal pieces. That's how small the shift is. For Alpha Centauri, the parallax angle is about 0.75 arcseconds. That is roughly the apparent size of a coin seen from about 5 kilometers away. Measuring an angle that small requires extraordinarily precise instruments and extraordinarily careful observations. For centuries, astronomers tried and failed to measure stellar parallax. They knew the principle worked. They understood the geometry, but their instruments weren't precise enough to detect such tiny angular shifts. The failure to measure parallax was actually used as an argument against the heliocentric model of the solar system. If Earth really orbits the Sun, critics argued, we should see the stars shift as we move. The fact that no shift was detected seemed to prove that Earth was stationary. What those critics didn't realize was that the stars were simply far more distant than anyone imagined. The parallax was there, but it was too small for the telescopes of the day to measure. It wasn't until 1838 that the German astronomer Friedrich Bessel made the first successful measurement of stellar parallax, determining the distance to the star 61 Cygni. Shortly after, Thomas Henderson measured the parallax of Alpha Centauri, confirming it as one of the nearest stars to our Sun. These measurements were landmark achievements in astronomy. For the first time in human history, we knew the actual distance to another star. Not an estimate, not a guess, but a measurement grounded in geometry and observation. And the distances they revealed were staggering. Even the nearest stars were trillions of kilometers away, far more distant than anyone had seriously imagined. Today, parallax measurements have been refined to extraordinary precision. The Hipparcos satellite, launched by the European Space Agency in 1989, measured the parallaxes of over 100,000 stars with unprecedented accuracy. Its successor, the Gaia spacecraft, launched in 2013, is mapping the positions and distances of over 1 billion stars in the Milky Way. Gaia can measure parallax angles as small as a few tens of micro-arcseconds, allowing it to determine distances to stars thousands of light years away. The distance to Alpha Centauri, 4.37 light years, is now known with extremely high confidence, thanks to these measurements. It's one of the most precisely determined stellar distances in all of astronomy, precisely because Alpha Centauri is so close that its parallax is relatively large and easy to measure compared to more distant stars. So the number we've been discussing isn't a guess. It isn't an approximation based on theory. It's a measured distance, determined by watching a star shift against the background of more distant stars as Earth swings around its orbit. The geometry is simple, the measurement is hard, and the result is sobering. Alpha Centauri is approximately 4.37 light years from our solar system. I use the phrase light year in that sentence as if it were a casual unit of measurement, something you can toss into a conversation without further explanation. But a light year is not a casual thing. A light year is the distance that light travels in 1 year. Light moves at about 300,000 kilometers per second. Every single second, light covers 300,000 kilometers. In 1 minute, it travels roughly 18 million kilometers. In 1 hour, just over 1 billion kilometers. In 1 day, about 26 billion kilometers. And in 1 year, traveling at this relentless speed without ever slowing down, light covers approximately 9.46 trillion kilometers. That's the distance of a single light year, 9.46 trillion kilometers, and Alpha Centauri is 4.37 of those. So let's do the arithmetic. 4.37 multiplied by 9.46 trillion gives us roughly 41.3 trillion kilometers. 41 trillion kilometers. That's the distance between our solar system and the nearest other star system. Just to write that number out in full, it's approximately 41,300 billion kilometers. 41 followed by 12 zeros. Every single one of those is a kilometer. A real, physical kilometer. The kind you could walk in about 10 minutes at a normal pace. And there are 41 trillion of them standing between you and the closest stars beyond our sun. Now, your brain just processed that number. You saw it, you acknowledged it, and you probably moved on because that's what brains do with numbers they can't visualize. They file them under big and move on, but I don't want you to move on. I want you to stay with this number for a while because the only way to understand the true scale of Alpha Centauri is to compare this distance to things you already know. So let's build those comparisons one by one. Start with the Earth and Moon. The distance from Earth to the Moon is about 384,000 kilometers. The distance to Alpha Centauri is roughly 107 million times that. If you lined up 107 million Earth to Moon gaps end to end, you'd reach Alpha Centauri. Remember, the Apollo astronauts took 3 days to cross one of those gaps. 107 million of them, each one a 3-day rocket journey placed back to back. That's the distance we're talking about. Now let's use the Sun. The Earth-Sun distance, 1 astronomical unit, is about 150 million kilometers. The distance to Alpha Centauri is approximately 276,000 astronomical units. That means the gap between us and Alpha Centauri is about 276,000 times larger than the gap between Earth and the Sun. The Earth-Sun distance already seemed enormous. It takes light over 8 minutes to cross it. A car driving non-stop would need 170 years. And you'd need to stack 276,000 of those distances end to end to reach Alpha Centauri. If the Earth-Sun distance were 1 inch, Alpha Centauri would be about 4.3 miles away. 1 inch for the distance to the Sun, and 4 miles for the distance to the nearest star. That ratio, from 1 inch to 4 miles, captures something essential about the emptiness of interstellar space. The things that seem enormous inside the solar system become almost nothing when measured against the gap to even the nearest star. Let's try another comparison. The entire orbit of Neptune, the outermost planet, has a radius of about 30 astronomical units. That means the solar system, as defined by the orbits of its planets, spans roughly 60 astronomical units from one side to the other. The distance to Alpha Centauri is about 276,000 astronomical units. That means you could line up about 4,600 solar systems edge to edge between us and Alpha Centauri. 4,600 copies of the entire region containing the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, all placed in a row, and you just barely reach our nearest stellar neighbor. Everything we've ever explored with spacecraft, every world we've photographed, every planet we've landed on, fits inside one of those 4,600 copies, and between each copy is nothing. Just empty space. Cold, dark, silent emptiness stretching for billions of kilometers before the next copy begins. If we include the Oort Cloud and extend the solar system to its full theoretical radius of roughly 100,000 astronomical units, or about 1.6 light years, then the distance to Alpha Centauri is only about 1.4 times the full diameter of our solar system, including the Oort Cloud. That sounds almost manageable when stated as a ratio, but remember that the Oort Cloud itself is so vast that no spacecraft has ever come close to reaching it. Voyager 1, after nearly 50 years of travel, has covered barely a fraction of the distance to the inner Oort Cloud. The full solar system, including the Oort Cloud, is already beyond anything we've traversed. And Alpha Centauri lies beyond that boundary, out in the true interstellar void, where the sun's gravity has no hold at all. Here's another way to think about it. Voyager 1 is currently the most distant human-made object. It's been traveling since 1977 at about 17 kilometers per second. It's now roughly 24 light hours from Earth. The distance to Alpha Centauri is 4.37 light years. A light year contains 8,760 light hours. So 4.37 light years is about 38,300 light hours. Voyager has covered 24 of those in 50 years. At that rate, Voyager 1 would need roughly 80,000 years to reach Alpha Centauri's distance. 80,000 years. Not 80 years. Not 800. 80,000. That's longer than modern humans have existed as a species on this planet. Anatomically, modern Homo sapiens appeared roughly 300,000 years ago. But behavioral modernity, the emergence of complex language, art, and abstract thought is generally dated to about 70,000 to 100,000 years ago. Voyager would need most of that span of time to reach the nearest star. You could have launched Voyager when humans first painted on cave walls, and it still wouldn't have arrived yet. Let me give you a scale model to hold in your mind. Imagine shrinking the sun down to the size of a basketball. At this scale, Earth would be a tiny grain about 2 millimeters across, sitting roughly 26 meters away from the basketball. That's about the length of a standard swimming pool. Jupiter would be a marble about 2 centimeters wide, sitting roughly 135 meters from the basketball. Neptune would be a small pebble about 800 meters away. The entire planetary solar system would fit within a sphere roughly 1 kilometer across. Now, where is Alpha Centauri in this model? If the sun is a basketball in this scale model, Alpha Centauri would be another basketball, or rather 2 basketballs and a marble representing the 3 stars, sitting roughly 7,000 kilometers away. 7,000 kilometers. In a model where the solar system fits within a kilometer, the nearest star system is 7,000 kilometers distant. That's roughly the distance from London to Mumbai. You've shrunk the sun to a basketball, you've compressed the entire solar system into something you could walk across in 10 minutes, and the nearest star is still on another continent. This is the reality of interstellar distance. It's not that the stars are far apart, it's that the space between them is almost incomprehensibly vast, relative to everything contained within a single stellar system. There's a reason this distance breaks human intuition, and it's worth understanding why. Your brain evolved to process distances on the scale of the environment that mattered for survival. Distances you could walk, distances you could throw a spear, distances you could see across an open plain. The maximum distance that was ever relevant to human survival was maybe a few dozen kilometers. The range a hunter-gatherer might cover in a day's travel. Our brains are extremely good at handling distances up to this scale. We can estimate them by eye, judge them by time, compare them intuitively. Even distances up to a few thousand kilometers, the scale of continents and oceans, are conceptually manageable because we have experience with travel over such distances, even if that experience is riding in an airplane. But beyond a certain point, our intuitive sense of distance simply stops working. The numbers get too large. There's no reference point, no lived experience that corresponds to millions or billions or trillions of kilometers. Your brain treats all sufficiently large numbers the same way. It files them under really big and moves on. This is why people consistently underestimate astronomical distances. When someone says Alpha Centauri is the nearest star system, the word nearest triggers an intuitive response. Your brain hears near and imagines something accessible, something reachable, something that isn't that far away. But the nearest star system is 4.37 light years away, 41 trillion kilometers, a distance so vast that our fastest spacecraft would need 80,000 years to cross it. The word nearest is technically accurate. Alpha Centauri is indeed the nearest, but it creates a psychological impression that is wildly, dangerously misleading. It makes people think the stars are close when they are anything but. Consider this. The ratio between the distance to the moon and the distance to the sun is roughly 1 to 390. That means the sun is about 390 times farther away than the moon. That's a big jump. But it's a jump your brain can handle. You can picture something being 400 times farther away than something else. The ratio between the distance to the sun and the distance to Neptune is about 1 to 30. Neptune is 30 times farther from the sun than Earth is. Again, a manageable ratio. 30 times is something you can conceptualize. But the ratio between the distance to the sun and the distance to Alpha Centauri is 1 to 276,000. The nearest star system is 276,000 times farther away than the sun. This is where intuition collapses. 276,000 is not a ratio your brain can process intuitively. It's too large. It doesn't connect to anything in your experience. You can write it down, you can calculate with it, but you can't feel it. And it's precisely this gap between knowing a number and feeling a number that makes the distance to Alpha Centauri so difficult to truly comprehend. And here's the thing that really puts this in perspective. Alpha Centauri is close, By the standards of the galaxy, by the standards of the universe, Alpha Centauri is absurdly, unbelievably, almost improbably close. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars spread across a disk roughly 100,000 light-years in diameter. Alpha Centauri is 4.37 light-years away. That's about 0.004% of the galaxy's width. In a galaxy that spans 100,000 light-years, our nearest neighbor is separated from us by a gap that wouldn't even show up as a visible line on a map of the Milky Way. If you drew the galaxy on a piece of paper, the Sun and Alpha Centauri would be so close together that you couldn't fit a pencil tip between them. They'd overlap. They'd be the same dot. And yet that dot, that invisible gap, represents 41 trillion kilometers of empty space. Most stars in the galaxy are much farther away than Alpha Centauri. The average distance between stars in our region of the Milky Way is roughly 4 to 5 light years. So Alpha Centauri happens to be almost exactly at the average nearest neighbor distance, but many regions of the galaxy have far larger gaps between stars. In the galactic halo, stars can be separated by hundreds of light years. In intergalactic space, between galaxies, the nearest star might be millions of light years away. We are fortunate, in a sense, to have a stellar neighbor as close as Alpha Centauri. And even this fortunate proximity amounts to 41 trillion kilometers of void. So this is where we are. We've established what Alpha Centauri is: a triple star system. 2 sun-like stars in a roughly 80-year orbit. 1 small red dwarf trailing along at a vast distance. We've established how far away it is. 4.37 light-years, roughly 41 trillion kilometers. We've understood how we know that distance through the painstaking measurement of a star's tiny shift against the background sky as Earth swings around its orbit. And we've compared that distance to everything familiar. 107 million times the Earth-Moon distance. 276,000 times the Earth-Sun distance. 4,600 solar systems laid edge to edge. 80,000 years of travel for our fastest spacecraft. 7,000 kilometers in a scale model where the Sun is a basketball. Every comparison tells the same story. The gap between us and the nearest star system is so immense that it breaks every intuitive framework we try to apply to it. The word nearest conceals a chasm of empty space so vast that crossing it represents one of the greatest challenges the laws of physics allow, and understanding just how uncrossable that chasm really is with anything humans have ever built or even seriously proposed building is exactly where we're headed next. So now you know the distance: 41 trillion kilometers, 4.37 light years, a gap so enormous that every comparison we built ended the same way, with your brain reaching its limit and the distance winning. But knowing a distance is one thing. Feeling what that distance actually means in practical terms, in terms of what it would take to cross it, that's something else entirely. Because this is where the title Nearest Star System reveals its deepest deception. It's not just that Alpha Centauri is far away. It's that even being the nearest, even being the absolute closest other star system to our own, it remains so fantastically remote that reaching it with anything humans have ever built or are likely to build in the foreseeable future ranges from absurdly impractical to flatly impossible. And understanding why requires looking at what we've actually achieved in space travel, what we've proposed, and what the laws of physics themselves have to say about the matter. Let's start with what we have right now. Our current best. The fastest spacecraft humans have ever launched in terms of sheer speed is the Parker Solar Probe. This spacecraft, launched in 2018, uses repeated gravity assist from Venus to tighten its orbit around the Sun, swooping closer and closer to our star with each pass. At its closest approach to the Sun, the Parker Solar Probe reaches speeds of about 192 kilometers per second. That's roughly 692,000 kilometers per hour. To give you a sense of how fast that is, at this speed, you could travel from New York to Los Angeles in about 20 seconds. You could circle the entire Earth in roughly 3.5 minutes. It is, by any human standard, an almost incomprehensible velocity. No human being has ever traveled anywhere near this fast. No human being ever will in the foreseeable future. The Parker Solar Probe represents the absolute pinnacle of speed that human engineering has achieved. So let's send it to Alpha Centauri. Hypothetically, let's ignore the fact that the Parker Solar Probe only reaches its maximum speed during close passes by the Sun and couldn't sustain that speed on a straight line trajectory to another star. Let's be generous and assume we could somehow maintain 192 kilometers per second continuously all the way to Alpha Centauri without slowing down. At that speed, how long would it take to cross 41 trillion kilometers? The answer is approximately 6,770 years, nearly 7,000 years. Let me put that in context. 7,000 years ago, humans had just invented agriculture in most parts of the world. The first cities in Mesopotamia were only beginning to form. Writing didn't exist yet. The wheel hadn't been invented. The pyramids of Egypt wouldn't be built for another 2,000 years. If you had launched the Parker Solar Probe toward Alpha Centauri, when humans first began farming, when civilization itself was just a seed in the ground, that spacecraft would still be traveling right now. It would still have centuries to go before it arrived. The entire span of recorded human history, every empire, every war, every discovery, every revolution, every poem and painting and scientific breakthrough, all of it fits inside the travel time of our fastest spacecraft to the nearest star. Now, let's consider Voyager 1. Since it's the spacecraft people most commonly associate with interstellar travel. Voyager 1 travels at about 17 kilometers per second. At that speed, reaching Alpha Centauri would take roughly 73,000 to 80,000 years, depending on the exact distance used in the calculation. 80,000 years. That number is so large it barely registers as a meaningful duration. 80,000 years ago, modern humans were in the middle of the last ice age. We were living in small nomadic bands, using stone tools, hunting mammoths, and giant bison across frozen landscapes. We hadn't yet reached the Americas. We hadn't built a single permanent structure. Everything that defines human civilization, agriculture, writing, cities, technology, science, art, law, medicine, all of it was still tens of thousands of years in the future. And if we'd launched Voyager toward Alpha Centauri at that moment, it would be arriving right about now. These numbers make something very clear. With the technology we currently possess, reaching Alpha Centauri is not a matter of decades or even centuries. It's a matter of millennia, tens of millennia. It's so far beyond any reasonable human planning horizon that it might as well be unreachable. No civilization in human history has lasted 80,000 years. Most empires last a few centuries at best. The idea of launching a mission that wouldn't arrive for longer than civilizations tend to survive is not engineering. It's hope bordering on fantasy. But perhaps we're being unfair. Perhaps current technology isn't the right benchmark. What about future technology? What about spacecraft that are faster, more advanced, designed specifically for interstellar travel? Surely human ingenuity can do better than Voyager's 17 kilometers per second. Let's look at what's been proposed. One of the most discussed, serious proposals for reaching Alpha Centauri is Breakthrough Starshot. This initiative was announced in 2016 by the late physicist Stephen Hawking and entrepreneur Yuri Milner. The concept is elegant and grounded in real physics rather than science fiction. The idea is to build a spacecraft that's not really a spacecraft in the traditional sense. It would be a star chip, a tiny wafer roughly the size of a postage stamp, weighing perhaps 1 to 4 grams. This chip would carry a camera, a small computer, basic communication equipment, and a light sail. A thin reflective membrane, perhaps a few meters across but only a few hundred atoms thick. The craft will be launched into orbit by conventional means. Then, from the ground, an enormous array of lasers would fire a concentrated beam of light at the sail. The pressure of that light, photon pressure, would push the sail forward. Because the craft weighs almost nothing, the acceleration would be tremendous. The proposal calls for accelerating the star chip to roughly 20% of the speed of light. That's about 60,000 kilometers per second. 60,000 kilometers per second. At that velocity, the craft could reach Alpha Centauri in approximately 20 to 25 years. Add another 4.37 years for the data to travel back to Earth at the speed of light, and you'd have results within about 25 to 30 years of launch. That's within a human lifetime. For the first time in history, we'd have a concept that could reach another star system and report back before the people who launched it grew old. This sounds extraordinary, and it is. But the engineering challenges standing between the concept and reality are staggering, and each one individually might prove insurmountable, let alone all of them together. First, the laser array. To accelerate a gram-scale craft to 20% of light speed within the few minutes before it moves out of range, you need an extraordinarily powerful laser system. The Breakthrough Starshot proposal calls for a ground-based laser array with a combined output of roughly 100 gigawatts. That's approximately the total electrical generating capacity of a medium-sized country focused into a single coherent beam aimed at a target a few meters across that's rapidly accelerating away from you. This beam would need to remain precisely focused on the sail for the entire acceleration phase, tracking a target that's moving faster and faster, accounting for atmospheric distortion, and maintaining coherence across the entire array. No laser system remotely approaching this power or precision has ever been built. The most powerful lasers in existence today produce a few petawatts in extremely short pulses, lasting femtoseconds, which is a completely different thing from sustaining 100 gigawatts continuously for several minutes. The technology gap between what exists and what Breakthrough Starshot requires is enormous. Second, the sail itself. The sail needs to be incredibly thin and lightweight, while also being highly reflective and able to survive being illuminated by 100 gigawatts of focused laser light. The energy density hitting the sail during acceleration would be immense. If even a tiny fraction of that energy is absorbed rather than reflected, The sail would heat up and vaporize instantly. The material would need to be almost perfectly reflective and incredibly resistant to thermal stress. No material with these properties currently exists. Researchers have proposed exotic materials and designs, but nothing has been tested at anything remotely close to the required conditions. Third, surviving the journey. At 20% of the speed of light, the Starship would be traveling at 60,000 kilometers per second. At this velocity, colliding with even a tiny grain of dust, something smaller than a grain of sand would release energy comparable to a small explosive. The interstellar medium is not perfectly empty. There are roughly 1 to 10 atoms per cubic centimeter in the space between stars, along with occasional dust grains. Over 4.37 light years, the Starship would encounter enough material that impacts become a genuine concern. The craft would need some form of shielding or deflection system to survive the journey, but adding shielding adds mass, and adding mass means you need more powerful lasers to achieve the same speed, which makes every other problem worse. Fourth, communication. When the Starship arrives at Alpha Centauri, it needs to send data back to Earth. It needs to transmit images and measurements across 4.37 light years of space using a transmitter that weighs less than a gram and runs on almost no power. Over that distance, any signal spreads out enormously. The energy reaching Earth from a gram-scale transmitter at Alpha Centauri's distance would be fantastically faint. You would need enormous receiving dishes on Earth, likely arrays of dishes working together to detect such a whisper of a signal. And even then, the data rate would be painfully slow. Sending back a single photograph might take days or weeks. The communication challenge alone is one of the hardest unsolved problems in the entire proposal. Fifth, aiming. The Starship accelerates to 20% of light speed and then coasts. There's no engine, no fuel, no way to make course corrections. Whatever trajectory it's on when the lasers finish pushing it is the trajectory it follows for the next 20 years. At 60,000 kilometers per second, even a tiny error in the initial aim would result in the Starship missing the Alpha Centauri system entirely, sailing past in the void millions of kilometers from any star or planet. The point in accuracy required during the acceleration phase would need to be extraordinarily precise. And remember, the Starship is being pushed by a laser beam from the ground through Earth's atmosphere while the Earth is rotating and orbiting the Sun. The targeting requirements are almost absurdly demanding. And sixth, even if everything works perfectly, the Starship flies past Alpha Centauri at 20% of light speed. It doesn't slow down. It can't slow down. There's no brake. Slowing down from 20% of light speed would require just as much energy as speeding up. And the Starship has no onboard propulsion system of any kind. It's a flyby mission. The Starship would scream through the Alpha Centauri system at 60,000 kilometers per second, and the entire window during which it would be close enough to take useful observations would last perhaps a few hours, maybe a day at most. Then it would continue on into the void, never to return, drifting through interstellar space forever. So, Breakthrough Starshot, the most credible and well-funded proposal for reaching another star, would at best send a craft the size of a postage stamp on a one-way flyby that takes 20 years, gives us a few hours of data, and requires technology that doesn't yet exist. And this is the optimistic scenario. This is the plan that scientists and engineers and billionaires are seriously working on because everything else is even harder. What about sending something larger? What about sending an actual spacecraft? One with instruments and communication systems, and perhaps even the ability to slow down and orbit a star in the Alpha Centauri system. Here, the physics becomes truly punishing. The fundamental problem is energy. Accelerating any object to a significant fraction of the speed of light requires an enormous amount of energy. And the energy required scales with mass. Breakthrough Starshot works in concept because the craft weighs almost nothing, a few grams, but a proper scientific probe might weigh hundreds of kilograms or tons. A crude spacecraft would weigh thousands of tons. The energy required to accelerate a 1-ton spacecraft to even 10% of light speed is approximately 450 quadrillion joules. That's roughly the total energy consumption of the entire United States for about 2 days, all concentrated into propelling a single object. For 1 ton, a crude ship weighing 1,000 tons would need 1,000 times more energy. And this is just to speed up. If you want to slow down at the other end, you need the same amount of energy again to decelerate. The total energy budget for a round trip is staggering beyond anything human civilization currently produces. Nuclear propulsion has been proposed as a way to achieve higher speeds. Project Orion, studied in the late 1950s and early 1960s, proposed propelling a spacecraft using nuclear explosions detonated behind it. Each explosion would push against a large plate at the rear of the ship, driving it forward. In theory, a nuclear pulse drive could achieve speeds of perhaps 3 to 5% of the speed of light. At 3% of light speed, roughly 9,000 kilometers per second, the journey to Alpha Centauri would take about 145 years. That's better than thousands of years, but it's still far beyond any single human lifespan. And the engineering challenges of detonating thousands of nuclear weapons behind a spacecraft while keeping the crew alive are, to put it mildly, non-trivial. Project Orion was shelved in the 1960s, partly due to the partial nuclear test ban treaty and partly because the engineering was simply beyond what anyone could realistically build. Nuclear fusion propulsion has also been proposed. Project Daedalus, a study conducted by the British Interplanetary Society in the 1970s, designed an uncrewed spacecraft powered by inertial confinement fusion. Tiny pellets of deuterium and helium-3 would be ignited by electron beams, producing thrust through controlled nuclear fusion. Daedalus was designed to reach Barnard's star, about 6 light-years away, in approximately 50 years, traveling at roughly 12% of light speed. But Daedalus would have been enormous. The design called for a spacecraft weighing roughly 54,000 tons at launch, most of which was fuel. 54,000 tons. That's heavier than a modern aircraft carrier. Launching that much mass into space, assembling it, fueling it with helium-3, which would likely need to be mined from the atmosphere of Jupiter, and then executing a 50-year uncrewed mission across interstellar space is so far beyond current capabilities that it barely qualifies as engineering. It's more like aspirational physics. These proposals all share one thing in common. They're designed for robotic probes, not people, and there's a reason for that. Sending humans to another star introduces an entirely different category of problems that go far beyond propulsion and energy. Because humans are not microchips. You can't shrink them to a gram. You can't shut them down for the journey and turn them back on at the destination. Humans need air, water, food, space to move, medical care, social interaction, and psychological stability. They need all of these things continuously for the entire duration of the trip. And for any realistic interstellar crossing with technology remotely resembling what we can imagine building, that duration is measured not in years, but in centuries or millennia. This is where the concept of the multi-generational ship enters the conversation. The idea is simple in principle. If the journey takes longer than a human lifespan, you build a ship large enough to support a self-sustaining community. People live on the ship, have children, grow old, and die. Their children grow up, have their own children, and continue the journey. Generation after generation lives out their entire existence aboard the vessel, each one a little closer to the destination than the last. The people who eventually arrive at Alpha Centauri would be the distant descendants of the people who launched, separated by dozens or perhaps hundreds of generations. The concept is simple. The reality is nightmarish. Start with the ship itself. To support a viable breeding population, you'd need at minimum several hundred people, and more likely several thousand to avoid genetic problems from inbreeding over many generations. Those people need living space, not just cramped quarters, but genuine habitable volume with room for agriculture, recreation, education, and governance. They need farms or hydroponic systems capable of producing food indefinitely using only recycled nutrients and energy. They need water recycling systems that work flawlessly for centuries. They need air recycling systems that never fail, because a single prolonged failure means everyone dies. They need medical facilities capable of handling every illness and injury that might arise over hundreds of years without resupply from Earth. They need manufacturing capability to repair and replace every critical system on the ship, because nothing built by human hands lasts for 1,000 years without maintenance. The ship would effectively need to be a self-contained world, a closed ecosystem that can sustain itself indefinitely without any input from outside. Earth's biosphere is the only closed ecosystem we know of that actually works, and it took billions of years of evolution to reach its current stability. It also has a mass of roughly 5.5 trillion kilograms and occupies the entire surface of a planet. Replicating even a tiny fraction of that stability in an artificial structure is a challenge we have never come close to meeting. The most ambitious closed ecosystem experiment ever attempted on Earth was Biosphere 2, a 3-acre sealed facility in Arizona that tried to create a self-sustaining environment in the early 1990s. It failed. Oxygen levels dropped dangerously, crops underperformed, insects died, species went extinct within the enclosure, and that was on Earth's surface with gravity, sunlight, and the ability to abort the experiment at any time. Now, imagine trying to do the same thing in a spacecraft, in zero gravity or artificial gravity, with no sunlight except what you generate artificially, no possibility of rescue, and no margin for error across centuries of operation. Then there are the human problems. How do you maintain social order on a ship for 1,000 years? How do you prevent conflict between generations who never chose this mission? The people who launched chose to go. Their grandchildren did not. Their great-great-great-grandchildren were born into a metal world they never asked to inhabit, traveling toward a destination they've only heard about in stories with no possibility of turning back. What happens when a faction on the ship decides they don't want to continue? What happens when resources run short and rationing becomes necessary? What happens when the social fabric frays after centuries of confinement? Every human society in history has experienced conflict, upheaval, and change. A multi-generational ship would be no different, except that on a ship, conflict can be fatal for everyone. A civil war on Earth is devastating. A civil war on an interstellar vessel is extinction. There's also the question of purpose. The people who launch the mission have a clear purpose. They're pioneers, explorers, the first generation of an interstellar journey. But what about the 50th generation? Or the 100th? These people were born on the ship. They'll live their entire lives on the ship. They'll die on the ship. The destination is an abstraction to them, a place their distant descendants might someday reach. How do you motivate a population to maintain a ship and a mission for a goal they will never personally achieve? How do you prevent apathy, despair, or outright rebellion from people who feel they were condemned to a life in a metal box by ancestors they never knew? These aren't engineering problems. They're human problems. And human problems are often harder to solve than engineering ones because they don't have clean solutions. You can calculate the thrust needed to reach a given speed. You can design a reactor to produce a given amount of energy. But you cannot design a social system guaranteed to remain stable for 1,000 years. No one has ever done it. No one knows if it's possible. And then there's the speed of light itself, the ultimate barrier. Because no matter how good our engines get, no matter how much energy we can harness, the speed of light stands as an absolute ceiling that physics will not let us break. This isn't a technological limitation. It's not like the sound barrier, which was once thought unbreakable and then was broken when we built faster aircraft. The speed of light is woven into the very structure of space-time. Einstein's theory of special relativity, published in 1905 and confirmed by over a century of experiments, shows that as any object with mass approaches the speed of light, the energy required to accelerate it further increases without bound. To actually reach the speed of light would require infinite energy, which is impossible. The universe simply doesn't allow it. This has been tested. Particles in particle accelerators are routinely accelerated to 99.999% of the speed of light. At these speeds, the particle's effective mass increases enormously. The energy required to push them even a tiny fraction of a percent faster becomes greater than the energy used to accelerate them through all the previous speed. The speed of light isn't a wall you can break through with enough force. It's an asymptote you can approach, but never reach. This means that even in the most wildly optimistic scenario, even if we developed a perfect propulsion system with unlimited energy, the absolute fastest we could ever send a crewed mission to Alpha Centauri would be just under 4.37 years. Because that's how long light itself takes to make the journey. In practice, no spacecraft would ever come close to light speed. Even reaching 10% of light speed would be a monumental achievement, requiring energy budgets that dwarf anything in human history. At 10% of light speed, roughly 30,000 kilometers per second, the journey would take about 43 years. That's within a single long human lifetime. An astronaut who left at age 25 might arrive at age 68. But building a spacecraft capable of sustaining 10% of light speed, keeping a crew alive for 43 years in the hostile environment of deep space, shielding them from radiation and micrometeorite impacts, providing food and water and air for decades, managing the psychological effects of total isolation from Earth. These are challenges so far beyond our current abilities that they might as well be magic. And there's another problem that people rarely think about. Even at 10% of light speed, you eventually need to slow down. You can't just arrive at Alpha Centauri at 30,000 kilometers per second and hope for the best. At that velocity, you cross the entire habitable zone of Alpha Centauri A in minutes. You'd fly past any planet before you could blink. If you want to actually enter orbit around a star, explore its planets, or establish any kind of presence, you need to decelerate. And deceleration requires just as much energy as acceleration. You need to burn just as much fuel slowing down as you burned speeding up. This roughly doubles your fuel requirements, which for a crewed vessel means even more mass, even more energy, even more engineering complexity. Some proposals try to solve this with magnetic sails that use the interstellar medium itself to create drag, or with laser beams from the destination system if one existed to slow the craft. But these are speculative technologies that exist only on paper. The honest truth, the truth that no amount of optimism can erase, is this. With current technology, reaching Alpha Centauri would take tens of thousands of years. With the most advanced concepts ever seriously proposed, it would take decades at minimum, and centuries more likely. With physics as we understand it, the speed of light imposes a hard floor of 4.37 years that no crewed or uncrewed mission can ever beat. The nearest star system, the closest stars to our sun in the entire galaxy, sits behind a wall of distance so immense that crossing it represents perhaps the single greatest physical challenge the universe presents to any technological civilization. Some science fiction offers ways around these limitations. Warp drives that compress space in front of a ship and expand it behind, effectively moving the ship faster than light, without the ship itself exceeding light speed through local space. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, is a mathematically valid solution to Einstein's field equations that describes exactly this, but it requires exotic matter with negative energy density, something that has never been observed and may not exist. Even if it does exist, the energy requirements might exceed the total energy output of an entire star. And there are severe theoretical problems involving causality. The possibility that faster than light travel would allow you to arrive before you left, creating paradoxes that physicists generally regard as signs that something is fundamentally wrong with the proposal. Wormholes, tunnels through space-time connecting distant points, are another theoretical possibility. They too are valid solutions to Einstein's equations. But keeping a wormhole open and stable would require exotic matter in enormous quantities. Natural wormholes, if they exist at all, would likely be submicroscopic and would collapse far too quickly for anything to pass through. Engineering a wormhole large enough and stable enough to fly a spacecraft through is so far beyond known physics that it belongs firmly in the realm of speculation rather than engineering. The universe, it seems, was not designed for easy travel between stars. The distances are too large, the speed of light is too slow relative to those distances, while simultaneously being too fast to ever reach for anything with mass. The energy requirements for even modest interstellar velocities are too enormous. Every pathway to Alpha Centauri runs into the same fundamental reality. 4.37 light-years is not just far. It's a distance that resists every attempt to cross it. A distance that the laws of physics have conspired to make it as difficult as possible to traverse. And this is the nearest star system. The closest one. The one that bears the label nearest as if that word implies some form of accessibility. If 4.37 light years is this hard to cross, imagine the stars that are dozens, hundreds, or thousands of light years away. Imagine the center of our galaxy at 26,000 light years. Imagine Andromeda at 2.5 million light years. The distance to Alpha Centauri is not just a measurement, it's a statement about the nature of the universe we live in. It tells us that the cosmos is built on a scale where even neighbors are separated by gulfs that mock our fastest machines and challenge our deepest understanding of physics. The nearest star system isn't near at all. It's simply the least impossibly far. So we've established the distance. We've established that crossing it is somewhere between absurdly difficult and physically impossible with anything humans have ever built or seriously proposed. But there's another dimension to this distance that most people never consider, and it might be the most profound one of all. It's not just about getting to Alpha Centauri. It's about what 4.37 light years means for communication, for connection, for any conceivable relationship between our solar system and the nearest star. Because even if you never try to send a spacecraft, even if you never dream of physically crossing the gap, even if all you want to do is send a message, a simple hello beamed across the void at the fastest speed the universe allows, the distance to Alpha Centauri still defeats you. Not completely, but in ways that fundamentally change what communication means. Light travels at 300,000 kilometers per second. Radio waves travel at the same speed, because radio waves are light, just at a different wavelength. Every form of electromagnetic radiation, visible light, radio, infrared, ultraviolet, X-rays, all of it moves at the same speed, 300,000 kilometers per second, the speed of light, the fastest speed anything in the universe can travel. And at that speed, a signal sent from Earth toward Alpha Centauri takes 4.37 years to arrive. Not 4.37 seconds, not 4.37 minutes, 4.37 years. If you pressed a button right now to send a radio message toward Alpha Centauri, that message would leave Earth at 300,000 kilometers per second. It would pass the moon in about 1.3 seconds. It would pass the sun's distance in about 8 minutes. Would reach Jupiter's orbit in about 43 minutes. It would pass Neptune in about 4 hours. It would cross the heliopause, the boundary where Voyager 1 entered interstellar space, in roughly 17 hours. And then it would keep going. For years. Through empty interstellar space, through the cold darkness between stars, carrying your message at the fastest speed the laws of physics permit. And 4 years, 4 months, and roughly 11 days after you press that button, your message would arrive at the Alpha Centauri system. Now imagine someone is there to receive it. Imagine, hypothetically, that there's an advanced civilization orbiting one of the Alpha Centauri stars. Or imagine that thousands of years from now, humanity has established a colony there. They receive your message, they read it, they compose a reply and send it back immediately. Their reply travels at the same speed, 300,000 kilometers per second, back across the same 4.37 light years. It arrives at Earth 4 years, 4 months, and 11 days later. The total round-trip time for a single exchange of information is roughly 8.74 years, nearly 9 years for one question and one answer. Think about what that means for any kind of meaningful communication. You send a message asking how things are going. 8 3/4 years later, you get a reply describing how things were going 4 1/3 years ago. The information is already old when it arrives. If you asked about a crisis, the crisis was resolved or worsened years before you heard about it. If you sent advice, the situation you were advising on changed completely before your words arrived. If you asked about someone's health, the person you asked about might have recovered, grown old, or died in the time it took for the exchange to complete. Every conversation would be a conversation with the past. Every reply would describe a world that no longer exists as described. You could never have a dialogue in any meaningful sense. You could only exchange monologues separated by years of silence. Consider the implications for governance. If humanity ever established a settlement at Alpha Centauri, that settlement could not be governed from Earth. Not in any practical sense. Any directive sent from Earth would arrive over 4 years after it was issued. By then, the political leadership on Earth might have changed. The policy priorities might have shifted. The directive itself might have been rescinded or replaced by a newer one that's still years away from arriving. The colony would receive instructions from a government that might no longer exist in the form it took when those instructions were sent. They'd be following orders from ghosts, from a version of Earth that has already moved on. The only viable option would be complete autonomy. The colony would need to govern itself, make its own laws, manage its own resources, resolve its own conflicts, and over time, inevitably, the colony and Earth would drift apart. Not physically, the distance would remain the same, but culturally. They'd develop different traditions, different perspectives, different solutions to different problems. The messages they exchanged would become more like letters between distant relatives who haven't seen each other in years, polite but increasingly disconnected. Within a few generations, the colony at Alpha Centauri and the civilization on Earth might share a common origin but little else. They'd be two branches of humanity growing in different directions, connected only by messages that take nearly a decade to exchange. Now, here's something that deepens this isolation further. We've been talking about Alpha Centauri as if it's uniquely far away, and in one sense it is. It's the nearest star system, the shortest interstellar crossing possible. But the truth is, Alpha Centauri's distance is not unusual. It's typical. The average distance between neighboring stars in our region of the Milky Way is roughly 4 to 5 light years. Alpha Centauri just happens to sit almost exactly at that average. The next nearest star after the Alpha Centauri system is Barnard's star, about 6 light years away. After that comes Wolf 359 at roughly 7.9 light years. Then Leyland 21,185 at about 8.3 light years. Sirius, the brightest star in Earth's night sky, sits at about 8.6 light years. Each step outward adds more years of light travel time, more years of communication delay, more distance that would need to be crossed by any spacecraft. And these are still our close neighbors. These are the stars in our immediate stellar vicinity. The Milky Way is 100,000 light years across. The stars we've been discussing, Alpha Centauri, Barnard's star, Sirius, all of them exist within a tiny bubble less than 10 light years in radius. That bubble contains maybe a dozen star systems. The galaxy contains hundreds of billions. To reach the center of the Milky Way, you'd need to travel 26,000 light years. A message sent at light speed toward the galactic center today would arrive 26,000 years from now. If someone at the galactic center sent a reply immediately, we'd receive it 52,000 years from now. The entire span of recorded human history, Every civilization that has ever risen and fallen, every war and peace, every invention and discovery, all of it fits comfortably within the round-trip communication time to the center of our own galaxy. And the Milky Way is just one galaxy among roughly 2 trillion in the observable universe. This is what the distance to Alpha Centauri is really telling us. It's not just a number, it's not just a fact about one particular star system. It's a window into the fundamental architecture of the cosmos. The universe is built on a scale where even neighbors are separated by years of light travel time, where even the shortest possible interstellar crossing represents a gulf that our fastest technology would need millennia to bridge, where communication at the maximum speed the universe allows still involves years of waiting for a single reply. The distance to Alpha Centauri is not an exception. It's the rule. It's the minimum distance the universe places between separate stellar systems. And that minimum is already almost incomprehensibly vast. This has implications for one of the deepest questions in science. Are we alone? The universe contains an estimated 200 billion trillion stars. Many of those stars have planets. Some of those planets orbit in habitable zones where liquid water could exist. The ingredients for life, carbon, hydrogen, oxygen, nitrogen, are among the most common elements in the cosmos. By every statistical argument, life should exist elsewhere, perhaps in enormous abundance, perhaps on billions of worlds. And yet, we've never detected a single sign of another civilization. No radio signals, no laser pulses, no megastructures, no artifacts, nothing. The universe appears to be silent. This is the Fermi paradox, and the distance to Alpha Centauri suggests at least part of the answer. Even if the galaxy is teeming with intelligent civilizations, the distances between stars make contact extraordinarily difficult. Our radio signals have been leaking into space for about a century. They've now reached all stars within roughly 100 light-years of Earth. That sounds like a lot, but the Milky Way is 100,000 light-years across. Our signals have covered a sphere 100 light-years in radius in a galaxy 100,000 light-years wide. That's a tiny fraction of the galaxy's volume, and those signals are getting weaker as they spread out. By the time our earliest radio broadcasts reach a star, even a few dozen light-years away, they're so faint they'd be virtually undetectable above the background noise of space. Any civilization hoping to pick up our signals would need extraordinarily sensitive equipment pointed in exactly our direction, at exactly the right frequency, at exactly the right time. And even if they detected us, even if a civilization at a star 50 light-years away picked up one of our radio broadcasts, think about the timeline. They'd be hearing a broadcast that left Earth 50 years ago. If they responded immediately, we wouldn't receive their reply for another 50 years. That's a 100-year round trip for a single exchange. You could ask a question and your great-grandchildren might hear the answer. For stars farther away, the delays become even more extreme. A civilization 1,000 light-years away would require a 2,000-year round trip. You could send a message when the Roman Empire was at its height and receive a reply around now. Any meaningful exchange of knowledge between civilizations separated by such distances would span centuries or millennia. Entire civilizations might rise and fall between messages. The civilization that sent the original message might not exist anymore when the reply arrives. You'd be communicating with ghosts or becoming one. There's something quietly staggering about applying this realization back to Alpha Centauri specifically. This is the nearest star system. This is the absolute best case for interstellar communication. And even here, a simple exchange takes almost 9 years. If the nearest star system is this hard to talk to, then the rest of the galaxy might as well be in another universe for all the practical difference it makes. The stars are islands, separated by oceans of time. You can see them glittering in the distance, but you cannot easily reach them, and even shouting across the water takes years. But let's shift perspective now, because there's something else. The distance to Alpha Centauri reveals something that goes beyond the practical challenges of travel and communication. It reveals the true nature of the space we live in. We tend to think of space as a backdrop, a stage on which stars and planets perform. But the distance to Alpha Centauri shows that space is not just a stage, it's the dominant feature of the universe. It's the main character. The overwhelming majority of the universe is empty. Not mostly empty, not largely empty, overwhelmingly, crushingly, almost entirely empty. The space between stars is a void of such completeness that it makes every other emptiness in human experience seem crowded by comparison. Consider this. Inside our solar system, within the orbit of Neptune, there are 8 planets, hundreds of moons, millions of asteroids, billions of comets, and 1 star. That sounds like a lot. But the volume of space contained within Neptune's orbit is roughly 2.7 times 10 to the 39th cubic kilometers. Almost all of that volume is empty. If you randomly selected a cubic kilometer within Neptune's orbit, the overwhelming probability is that it would contain nothing. No rock, no gas, no dust, just vacuum. And this is inside the solar system, the densest part of our local space. The region where matter actually accumulates under the sun's gravity. The space between stars is emptier still by orders of magnitude. Between the outer edge of our solar system and the nearest reaches of the Alpha Centauri system, there is essentially nothing. A few stray atoms of hydrogen per cubic centimeter, the occasional grain of interstellar dust, perhaps the odd rogue object drifting through the void. But for all practical purposes, it's empty. 41 trillion kilometers of nothing. If you were somehow placed in the middle of this void, halfway between the Sun and Alpha Centauri, roughly 2 light years from either star, what would you see? You'd see stars, thousands of them, scattered across a black sky in every direction. The Sun would be one of the brighter ones, but it wouldn't dominate the sky the way it does from Earth. It would be a bright point of light, brighter than most other stars visible from this vantage point, but still just a point. You wouldn't see any planets around it. They'd be far too small and faint to resolve at 2 light years. Alpha Centauri would appear as another bright point on the opposite side of the sky, perhaps appearing as one very bright star, or, if your eyes were sharp enough, as 2 points very close together representing A and B with Proxima, too dim to see at all. Around you in every direction would be an ocean of darkness punctuated by distant pinpricks of light. Each one a star, each one surrounded by its own vast sphere of gravitational influence, each one separated from its neighbors by light years of void. You would be floating in the space between islands, surrounded by more nothing than most human minds can comfortably contemplate. The loneliness would be absolute. The nearest solid object in any direction would be trillions of kilometers away. The nearest warmth, the nearest light source close enough to warm your face, would be years of travel away, even at the speed of light. This is the space that separates us from Alpha Centauri. This is what 4.37 light years actually looks like. Not a distance on a chart, not a number in a textbook, but an immense, silent, lightless gulf of almost perfect emptiness that stretches between our sun and the nearest other star for trillions of kilometers in every direction. And every other star in the galaxy is surrounded by a similar gulf. The Milky Way is not a dense collection of stars packed shoulder to shoulder. It's a sparse scattering of tiny points, separated by enormous voids. If you shrank every star in the galaxy to the size of a grain of sand, the nearest grains would still be kilometers apart. The galaxy is mostly nothing. The universe is mostly nothing. And the distance to Alpha Centauri, that 41 trillion kilometers of void, is simply the smallest sample of that nothing that exists between any two stellar systems from our vantage point. Understanding this changes something about how you see the night sky. Before you understand the true scale, the stars look close. They look like they're all at roughly the same distance, as if they're painted on the inside of a dome just above your head. Even after you learn that some stars are farther than others, they still appear as a collection, a community, a neighborhood of lights scattered across the darkness. But when you truly grasp what 4.37 light years means, when you understand that even the nearest star is separated from us by a chasm that would take our fastest spacecraft millennia to cross, the night sky transforms. Those points of light are no longer a neighborhood. They're islands. Isolated islands separated by vast dark oceans. Each star burns alone in its own pocket of space, separated from its nearest neighbor by light years of emptiness. The galaxy is not a crowded city of stars. It's an archipelago scattered across an ocean so vast that most islands can never be reached from any other. And yet, there's something else that emerges from this understanding. Something that isn't bleak at all. Because the distance to Alpha Centauri doesn't only reveal how isolated we are, it also reveals how extraordinary it is that we know any of this at all. Think about what it means that a species living on one small planet, orbiting one ordinary star, has figured out the distance to the nearest stellar system with precision. We know that Alpha Centauri is 4.37 light years away. We know it's a triple star system. We know the masses, luminosities, temperatures, and orbital parameters of all three stars. We know that Proxima Centauri has planets. We know the approximate size and orbital period of those planets. We've measured the system's motion through the galaxy. We've calculated when it will be closest to us and when it will drift farther away. All of this knowledge was gathered from the surface of a planet that is 41 trillion kilometers away from the system in question. We've never been there. We've never sent anything there. We've never touched it or sampled it or orbited it. Everything we know about Alpha Centauri was learned by collecting the faint light that traveled across 4.37 light years of empty space and arrived at our telescopes after a journey lasting more than 4 years. That's remarkable. That's one of the most impressive achievements of any species on any planet anywhere in the universe, as far as we know. The distance to Alpha Centauri is humbling, yes. It shows us how small we are, how isolated, how limited by the fundamental structure of space-time. But it's also a measure of our ambition and our capability. We can't cross that distance. We can't even come close with current technology. But we can measure it. We can study what lies on the other side. We can understand the physics that makes the crossing so difficult. And we can dream about doing it anyway, not because it's easy or practical, but because the desire to reach beyond our horizon is one of the defining traits of our species. Every generation of humans has looked at a boundary and wondered what lay beyond it. Early humans wondered what was beyond the next ridge, beyond the river, beyond the ocean. Each time we push past a boundary, we found a larger world than we'd imagined. The distance to Alpha Centauri is the latest boundary, and in many ways the most daunting one. It's not a ridge you can walk over or an ocean you can sail across. It's a void so vast that even light needs years to cross it. And what lies beyond it is not just another continent or another island, but another star, another system of worlds, a place that formed independently from our own, burning with its own light for billions of years. If we ever do cross that distance, whether with a gram-scale chip accelerated by lasers or with some technology we haven't yet imagined, it will represent the single greatest journey in human history. Greater than any ocean crossing, any continental exploration, any journey to the moon. Because the distance to Alpha Centauri is not just longer than those journeys, it's fundamentally different. It exists on a scale that dwarfs everything humans have ever experienced by a factor of millions. Crossing it would mean leaving the sun's domain entirely, traveling through the interstellar void for years or decades or centuries, and arriving at a place that no human eye has ever seen up close. It would mean proving that the gaps between stars, however vast, are not permanent prisons. That the universe, for all its emptiness, can be traversed by creatures small and determined enough to try. But even if we never cross it, even if the distance to Alpha Centauri remains forever a boundary we measure but never breach, understanding that distance matters. It matters because it tells you the truth about where you live. You live on a small rocky planet orbiting an ordinary star that happens to sit about 4.37 light years from the nearest other star system. You live in a universe where the spaces between things are almost incomprehensibly larger than the things themselves. You live in a cosmos that is mostly void, mostly dark, mostly silent. And within that cosmos, on one small world, you are alive and aware and capable of understanding all of this. That's not nothing. That's extraordinary. So the next time someone tells you that Alpha Centauri is the nearest star system, you'll know what that really means. It means 41 trillion kilometers. It means 4.37 years at the speed of light. It means 80,000 years for Voyager. It means nearly 9 years for a round-trip message even at the fastest speed the universe allows. It means a gulf so vast that it contains more empty space than most people will ever contemplate. It means that even the nearest stars are separated from us by distances that challenge the limits of physics, engineering, and human imagination. The word nearest doesn't mean close, it means the least far. And the least far is still staggeringly, almost incomprehensibly, beautifully, terrifyingly far. When you look up at the night sky tonight, find the southern horizon if you can. If you're in the right part of the world, you might see Alpha Centauri shining there, one of the brightest points of light in the sky, looking for all the world like it's just overhead, just out of reach. But now you know the truth. That light left Alpha Centauri 4.37 years ago. It's been traveling at 300,000 kilometers per second since before you had whatever thought you had 4 years ago. It crossed trillions of kilometers of empty interstellar space. It passed through the outer reaches of the sun's gravitational domain. It entered our solar system. It fell through the orbits of the outer planets, past Mars, past the moon. It slipped through Earth's atmosphere, and it landed on your eye. A photon that has been traveling for 4 years and 4 months, carrying with it the image of a star as it was years ago, not as it is right now. You're looking into the past. You're seeing across a distance that defies human comprehension. You're connected by a thread of ancient light to the nearest star system, a place that might as well be at the edge of forever. The universe is vast. The distances between stars are enormous. Even the nearest crossing, the shortest possible journey from one star to another, represents a challenge so immense that it sits at the very edge of what physics allows. Alpha Centauri is close, but close means something very different when you're talking about stars. Close means 41 trillion kilometers. Close means millennia of travel. Close means years of light-speed communication delay. Close means a void so deep and so dark and so empty that it stretches beyond the reach of every intuition your brain possesses. And yet, the light still comes. Every night, photons that left Alpha Centauri years ago arrive at Earth, carrying information about a place we've never visited and may never reach. Those photons are proof that the distance, however vast, is not infinite. It can be measured, it can be studied, it can be understood, and maybe someday it can be crossed. But for now, it stands as it is. 4.37 light years of silence, darkness, and empty space. The true scale of Alpha Centauri, the nearest star system, and the farthest place we've ever called close. Thank you for joining me on this journey tonight. If you found this exploration meaningful, a like or subscribe would genuinely help this channel continue making these deep explorations of the cosmos. And the next time you look up and see the stars, remember what lies between them. Remember that even the closest, one is separated from us by a distance that humbles everything humans have ever built. Remember that the universe is vast beyond comprehension, and that you, standing on one small world, can understand that vastness. That's not a small thing. That's one of the most extraordinary things in the entire cosmos. Sleep well tonight, under the light of distant stars. Alpha Centauri is out there, burning steadily, 4.37 light years away. Close enough to see, far enough to break your heart, and beautiful enough to make you look up anyway. Good night.